tiny bit just to finish what we were doing last time, and then we go to DG schemes, which is much more geometric. So we were trying to do this notion of étal covering or derived stacks. So we said that there is a family. If I have a family of morphisms like this, from some A dot to A dot I, morphisms of simplicial commutative rings. This family is a family of these things is an étal covering of each if A dot, the morphism to A dot I for each I is étal. Is étal in the sense that I define in this category of simplicial commutative rings. We know what the morphism, étal morphism of rings are. And furthermore, the family of functors, which you obtain as, so for each one of these guys, you can define this left derived pullback, if you like, over the A dot modules to A dot I. So this is some functor that takes you from the homotopy category of the simplicial A dot modules to the homotopy category of the simplicial A dot I modules. And these are, you have a family of these things for your family, and you wanted this to be conservative. That's that. And so by definition, the étal topology on this homotopy category of derived affine objects is the topology for which covering sieves are given by these étal covers. Okay? Are given by the one generated by étal covering families. Okay, so this is that, and then similar to before, for any x in this category of derived affine objects, this was, if you remember, this was the opposite to the category of simplicial commutative rings. The same way that we have category of commutative rings, the opposite category is the spectrum of those rings. So commutative rings has an opposite category, and those are the specs of those rings. Same thing. But these are derived affine objects, I call them, because these are categorical objects. And then off of these, we construct over this category some simplicial presheaf, taking values in simplicial sets. And that sheaf is given as, by the unit of functor, basically. And then that sheaf eventually becomes, if you like, a stack, a scheme, things like that. Okay. So, but this is the underlying category. That's why I never say derived affine schemes, but I call that derived affine object. So, similar to before, for any x in this category, we define an étal topology. topology on homotopy category of all the derived affine objects you can have over that particularly given object in this category. So this category is the category of all other derived affine objects which map to this terminal object in the category. So that the Etal topology on homotopy category of derived affine objects can be used to define homotopy sheaves for objects in this, let's say, objects in the homotopy category of derived affine. And this is something I call derived affine hat. These are the pre-stacks. These are the ones that satisfy some extra condition. Okay, so if you look at the video of the last session, you can see this definition of this derived affine objects. This hat is the pre-stack ones, the ones that satisfy the pre-stack condition. And this homotopy category embeds as a full subcategory in the homotopy category of simplicial pre-sheaves on over this category without a hat. It is this category that via certain extra conditions will give you honest categorical notion of stacks or derived stacks or derived schemes. Okay, but today we're not going to spend much time on these things. We are going to now move to DG world, but to just finish what we did last. So let F be a functor from this category, the opposite category, to simplicial sets. Be an object in this category. Okay. So in particular, F sends, what does it do? Sends an equivalence in here to equivalences in the same category of simplicial sets. Equivalences in here. Now consider a pre-sheaf of sets, which is defined by x being sent to pi 0 of the fiber of f over that x. Okay, this pre-sheaf sends equivalences in this category derived affine to isomorphisms in the category of just sets. It's the pi 0 of those things. Pi 0 of those things are groups, but they have underlying sets. In set, and it factorizes. And so it factorizes as a functor, which I would call pi 0 of f. Which I would call pi 0 of f. The pre-sheaf of the pi 0 of F, which sends you from homotopy category of the derived affine objects, opposite of that category to set. This is basically a functor, which is defined by this tree sheaf for this functor of functors. And you can understand it exactly as soon as you look at the fiber of F over some point in the base category, which is some derived affine object. So, so this, in the same way, we can define a presheaf of groups on category of derived affine objects over a given one, and which sends and something like F, an object of this category, which is given by a map from a derived affine object to the terminal fixed derived affine object X. It sends this guy to pi I. Remember that originally in the first sessions or so, we actually defined this presheaf of fundamental groups of our category. And this is basically that. So this one is the zero fundamental group, and these are the higher fundamental groups. Remember that for these ones, we didn't need any fixing a base point, and for these ones, we defined them exactly like before. So this would be f of y, and we would pull back some zero simplex in X. So I say bridge of groups, we send this to that, where for X in derived affine and S in the zero simplex in here. Like, when you construct higher fundamental groups, you need to fix a base point around the point. So. But here, for these objects, you need to pull back that zero simplex to the other objects. Why? Okay, so this we are familiar with again from the first sessions. Again, this presheaf sends equivalences to isomorphisms, and thus induces a functor. Again, the functor of the higher fundamental groups, similar to the pi zero presheaf that we defined over there. This functor, what it does, it takes some functor and a zero simplex S, it defines a sheaf, and then what that is, it sends you from here, from this opposite category to the category of sets. Okay, so you have some presheaf over this category which understands higher fundamental groups. Remind yourself, why is it that we are putting these abstract things in here? Because, for instance, when we work with actual objects in these categories, like when we were defining one stacks and two stacks and so on, it was the fundamental group that was understanding the connectedness of that stack, and then understanding somewhat, automorphisms between objects, automorphisms of the objects, and then automorphisms to automorphisms of the objects, and so on and so forth. So these are exactly the same thing. But this time, over the category of affine objects, over superficial categories. Another thing which is different than the past is that we are working with objects in here, derived affine objects. So whenever we do this, we could have the notion of equivalence in here, because our simplicial commutative rings also can have the notion of equivalence. Okay. The associated sheaves pi 0 of f and pi I of f and s are called homotopy sheaves. Homotopy sheaves of f. Okay. Imagine that in the language of whenever, at least for me, whenever I would like to understand the literature in this subject, I think of these infinitesimally and homotopy. The notion of homotopy translates to homology, cohomology. Think about a stack scheme and think that you have a sheaf of somewhat local systems that you define on that stack, and it measures the cohomology. So, for instance, moduli stacks are good. Higher cohomology groups associated. So, okay, so these are defined for f from opposite category group simplicial sets, sending equivalences, these sheaves, equivalences to equivalences. Oh, very good. All right, so now definition, we're almost done. So finishing things left from the last slide. So definition, let's see. Okay, definition, let f to f prime now be a morphism. Be a morphism of pre-sheaves on this derived category. And one, the morphism f is a local equivalence. Is a local equivalence if it satisfies certain conditions. One, that the induced morphism pi 0 of f to pi 0 of f prime is an isomorphism, as an isom of sheaves in the category that these sheaves live in, and that's the homotopy category of the derived affine objects that these sheaves live in. Okay. So then you can have the notion of equivalence, local equivalence for any x in category of derived affine objects and any s, a zero simplex of the simplicial set which you obtain by looking at the fiber of the functor f over x, and any I bigger than 0, the induced morphism from pi I of f centered at s to pi I of f prime centered at f of x zero simplex thing is an isomorphism. Is an isomorphism. Okay. Whereas this isomorphism, now this is different. Isomorphism in here, right? Because I'm pulling back the zero simplex from a given zero simplex of a given derived output object. Okay. So there's that, and then there is this extra condition. Oh, I think yes, we are done. This is the conditions that need to be satisfied for the morphism to be a local equivalence. Now, second statement is that the morphism is a local cofibration. Okay, so what's a local cofibration? The local cofibration, if it is a cofibration, in it has the right different properties, and three, the morphism is a local fibration if it has the left, I mean this is almost, if it has a left lifting property. Lifting property with respect to every local cofibration, which is a local equivalence, and local equivalence is the condition that I defined over here. Okay, and now here is the final thing. We are doing all of these things because we have constructed these sheaves, three sheaves over this category, and so definition, an object F in simplicial, in the category of simplicial presheaves. These are presheaves over the category of derived affine objects with sections given by simplicial sets. It's called a stack or a derived stack, not a pre-stack, but a stack. If it satisfies conditions 1 and 3, 2 and 3. Furthermore, stacks require to satisfy. Remember that when we had the stack before, it satisfies certain gluing condition when we defined it before. It needs to satisfy the following things. So maybe I call them 1 prime. One is that for any x in this derived affine category, the simplicial set simplicial set f of x needs to be fibrant. 2 is that 2 prime is that for any morphism x to y, for instance, in derived affine category, the induced morphism is an equivalence. The induced morphism, well, is this correct? Yeah, is an equivalence of simplicial sets for any given by an equivalence, right? Otherwise, this doesn't make sense. By an equivalence, the induced morphism f of x goes to f of y. Then the third one is this hypercovering or the gluing condition of the stacks over the finer and finer basically covers, which is for any x in derived affine objects and a tall hyper covering, let's call that h dot x. If you remember, I told you that hypercovering or atal hypercovering is really the categorical notion for the check cover or the check nerve. Same way that for a topological space you can construct this check nerve for an object in the category of derived affine objects, so this df, you can construct something that behaves very similar to check nerve, and that's the hypercover. And the natural morphism f of x to homotopy limit, which I reminded you last time. Homotopy limit over these simplices f of hn is an equivalence of So one thing I would like to say is, after this, what we call the derived algebraic stack is very similar to the previous one. This already is over the category of simplicial commutative rings. So you can have the notion of n derived stacks, 1 derived stacks, and just the derived scheme. And the derived scheme is the zero truncated object, where your stack has a fibrant model whose higher homotopy groups are vanishing. It's just like itself. And then you have 1 stack, 2 stacks, and so on and so forth, depending on how many of these fundamental groups, depending on the order of vanishing of the higher and higher homotopy sheets of that stack, which are basically locally fundamental groups.
So we know that for simplicial sets, a map between two fibrant objects is a homotopy equivalence. Is a homotopy equivalence if and only if it induces isomorphism on all homotopy groups.
That's right.
So is this same for derived stacks?
Yes, that's right.
So is this trivial?
Fiber-wise, no, but you need to show it, but fiber-wise it is the same. You fix an object in the base, and then you look at the morphs of the stacks, you look at the fiber over that object, and then you can discuss it exactly what you said. Okay, so this is the notion of derived stacks, but we are not going to just work with any derived stacks. We are going to make it very, very geometric and as close as possible, maybe first order neighborhood of regular algebraic geometry by moving now to the world of DG schemes and DG stacks. So not only now we are trying to work with simplicial commutative rings, but we are actually giving them extra condition, extra structure of differentially graded rings. And then we define things, spaces or schemes or stacks over that. So let us move to that category. It's actually a big deal to, I mean, it's not a big deal, I mean, it's work, you need to do work to show that. When I'm defining this thing right now for you, you will see that it is more geometric than topological, but you need to actually work hard to show that this whole construction is compatible with the construction of derived affine schemes over the differentially graded rings. In some sense, the construction over differential graded rings, as you will see, is easier to understand. But you need to work to show that this is the same. I think I looked at papers of Kai Behrendt. He has written beautiful papers on this. Derived schemes, DG schemes actually, DG algebras and DG schemes, and he shows that one can be applied by the other. Okay, so let's go to DG vector spaces, algebras, and modules first. Okay, so that's what we would like to do. By a DG, or differentially graded, which from now on we will call DG. By differentially graded vector space, we mean a graded vector space. Let's call it something C dot, for instance. Okay, graded vector space C dot with a differential of degree plus 1. So I apply differential to the graded pieces and it shifts their degree by 1. If C dot is a complex, and Ci A is some element of the ith graded piece, then we can define a notion of, notion of the degree of the A. So we can define some notion of degree, and often it is overlined, and this will be defined by I. Keeps track of the weighted degree of that element in the differentially graded vector space. Now, if C dot is a complex, and is a complex, then we write H star of C dot for the graded space of cohomology. It's a complex cohomology of this C dot. We can take the cohomology at each degree, and we will also use a notation which is, if I put C dot with this sharp thing below, it means that I'm not going to think of it as the one with the differential maps. I'm just think of this as a graded vector space with the trivial maps. Okay? So this is going to be for the graded vector space space obtained from C dot by forgetting the differential. Okay, so I mean just a graded vector space given as a complex, and these are the usual things that we can do. Now, what is the morphism between these things? Some of the properties. So, a morphism f from C dot to D dot, okay, of complexes is called a quasi-isomorphism if it induces, if H star of this morphism, which is a map from the graded cohomology group of C dot to the graded cohomology group of D dot, is an isomorphism. Yes. Isomorphism in each degree. Exactly like quasi-isomorphism of objects in the derived category. Objects in the derived category are also graded objects, in fact. They are Z-graded objects. Right? But I mean, this time, we are not just naively thinking about just the grading. The gradings are related to one another by the differential. Okay? And the differential satisfies d squared equal to 0. That is the most important part. If you take an object in the derived category with respect to Z grading, you don't have such a notion necessarily. So it's kind of different, but
Sorry, are we also Z grading or Z grading?
yeah. Yes. Yes, that's right. So now, what do I want to say? So this is an isomorphism. Now, a definition. This is about graded vector spaces. Now let's talk about, this is the most linear, most naive thing that we can define. Now let's work on algebras, modules over algebras, and so on and so forth. So definition, differentially, a DG K algebra, a dot is a graded K algebra, which we write as something like this. So this is the sum over the pieces, like that, endowed with differentials. Endowed with differentials. So differential again takes you from A dot to itself, where you again of degree, it has degree plus 1. This is about algebras. So degree plus 1. So this would be a degree plus 1 monomorphism. Monomorphism of K vector spaces. K vector spaces satisfying d squared equal to 0. The most important property of differential graded algebra is this part, d squared equal to 0, and the graded Leibniz rule, and the graded Leibniz rule, which is what? Well, d of AB, we want it to be d of A times B plus minus 1 to the degree of A, where it sits in the graded algebra, or the underlying k-graded vector space, d of B. When you move the derivative, you need to scale it by the sign of A, by the degree of A, or the sign of A. So we use the notation A dot, again, like before, for A dot for underlying, so let me see. We use the notation A dot sharp, like before, for underlying K vector space. Vector space, and in fact A dot is the underlying K vector space of A dot together with the differential. But the underlying differentially graded K vector space, or K vector space, naive K vector space. The underlying graded K vector space, sorry, not differential, because the differentials are going away. Graded. K is the underlying field. Okay, so note for A dot, the homology vector star of A dot, kernel of D, modulo D, image of D, is a graded, like before, is a graded K algebra. Yes, like the K vector spaces where you can take the cohomology here, for the K algebra you can take the cohomology. And the degree 0, the cohomology H0 of A dot is a subalgebra of the A dot. So it's a subalgebra of A dot. Subalgebra of H star. Just the subalgebra of A dot. So I tell you what I mean. So if A dot is concentrated in non-positive degrees, then it is the case. Positive degrees. Then there is a morphism of BG algebras which takes you from A dot to H0 of A dot. Okay. Now, again, so these are differentially graded algebras, and you can now define modules over these algebras. Because, you would like to define schemes and stacks over differentially graded algebras and then sheets of functions on them. These are locally modules. So modules. e.g. differentially graded module m dot over the DG algebra A dot is a left graded left module. It's a left graded A dot sharp module. So before being a module, and every time it's a module going to be a module, over the underlying graded K vector space, and then it needs to be compatible with the differentials. That's why it's going to be a module over here as a left graded module, which we call that endowed with a differential on this module, D defined on this module M dot. And so this is the one that takes this guy to itself of degree plus 1. Okay, and all I need to tell you, so what is that? It means that that is a degree plus 1 homomorphism of graded K vector spaces. K vector spaces satisfying compatibility, basically, relation. So what happens if I want to take a differential of some element of this module in the differentially graded ambient ring? So this needs to satisfy, first of all, this condition, d square, and then add graded Leibniz rule. Graded Leibniz rule, which is the d of m dot applied to a times m. It's going to be, again, d of a times m plus minus 1 to the degree of a d m dot of m. Again, you scale it by the sign of that element of the DG ring. So this is for A in underlying ambient K vector space and little m in the underlying K vector space of the module M dot. Note that the cohomology, or the graded cohomology group of this guy M dot is a graded module, over graded, let's put it this way, as a graded H star of A dot module. This algebra H star of A dot acts on it. So it's a module of that algebra. Okay, any questions? So now, so this again, there's a proposition definition is that I'm not going to prove it. So if A dot is a Z-graded associative algebra, and M dot is a left A dot module in the sense I defined above, left A dot module, then G, which sends you from Mi to Mi plus 1, is A0 linear. In fact, this is not so hard to see because of the structure that you have there. A0 maps to A1 and so on and so forth. So you can actually see the superposition without. Now, you can have modules over DG ring, and you can look at the tensor products and look at morphisms and so on. Let's discuss those things. These are just the basic stuff. The tensor product of A dot modules, let's say M dot and N dot, has underlying again graded A dot sharp modular structure, which in this case the A dot sharp module would be M dot sharp, which is a module over A dot sharp, N dot sharp. This is the underlying module together with differential mass. Every time we talk about modules over a DG ring, you will talk about just the graded pieces, and then you need to tell me how do they behave in terms of the differential of the ambient DG ring. So this is the underlying module, or the graded module, and together with and the differential is given by, now I need to tell you what is the differential of a tensor product of two modules. So the differential on the tensor product of two modules M dot and dot of two elements of these modules, this being an element in M dot and this being an element in N dot, okay, is given by d of M dot acting on N, tensor N, plus minus 1 the sign of M d of M dot, M tensored with d over N dot of N. It's natural, right? I mean, you can imagine. You could have guessed it. It's very natural. Okay. Now, the inner homomorphisms can be defined. So inner homomorphism over A dot of between M dot and N dot. Also, the inner hom can be has underlying again module structure, so has underlying graded A dot sharp module, which is given by over A dot of Mn sharp. And what is that? Well, it's going to be having something very similar to all possible homomorphisms of all degrees between M and N, all A dot morphisms between M and N, M dot and N dot. And that is going to be N, hom N, hom N, A dot sharp, M dot sharp, N dot sharp. exactly like how you define inner harm between two bundles and things like that, or two complexes of vector spaces. All of them for all of them, in all degrees.
But they require A as commutative. As A commutative.
Differential, yes.
A as itself to be commutative.
Yes. Okay. Yeah, that's a good point actually. It needs to be assumed. Okay. And the differential on this, and the differential, again, I need to tell you how to take the differential of a homomorphism between modules, but these are all graded modules. They need to come with their differential. So if I wanted to do that, I would just say differential on n dot of some phi of a little m is going to be the differential on hom m dot n dot of phi of m plus minus 1 degree of phi of d n dot of n. What is phi? This is for m. Oh, so this I wrote here, m and m dot. Okay, so this is for that. And phi is in an element of this homomorphism over a dot. Okay, so this is very interesting, isn't it? I think this is something that you can. These are these little things that one can practice later. And this is how it is defined. It's compatible. In fact, the K vector space. The K vector space of differentially graded A dot module homomorphisms. Homomorphisms, let's say from m dot to m dot, is the set of zero cycles in hom A dot m dot to m dot. So right, really, let us remove this comment because it's easier. I've already defined it. So, okay, so I think this is that. Now, one thing is that note that remark differentially the DG A dot modules form an abelian category. Form an abelian category with kernels and co-kernels. It's closed undertaking the kernel and co-kernel, and images and rexons and direct sums. Taken degree-wise. all of these, of course, you take degree-wise. Kernel between these things, these are towers, and you take kernel degree-wise. And that gives you the kernel between the homomorphism between the two A.DG modules. Okay, so that's that. Then, how much time? So, okay, so we have half an hour, and I think that's enough. So, in fact, the category of DGA modules is an abelian subcategory of the category of complexes of vector spaces, that we know how to define. It's the abelian one, an abelian subcategory. So that category is much bigger. We have the following formulas. So some properties of inner Helms. These might be familiar with you if you have worked with, complex vector spaces or objects in the derived category. You might recognize these properties. So homomorphism, inner Helm over A dot algebra between M dot and N dot times over A dot with another A dot module is the same as Helm over A dot modules M dot N dot times P dot over A dot. So we have seen it before. And Helm over A dot of M tensor N over A dot, and P dot is the same as Helm over A dot of M dot Helm over A dot of N dot P dot. This also holds true. When you want to move this one to here, it becomes a homomorphism. We have seen this before, actually. I mean, if you have worked with objects, the complexes, in the category perf, for instance, or the objects in the draft category, you have seen this before. Okay? And but even simpler than that, you have seen it probably advanced linear algebra or something like that. In algebra. So this is for differentially for DG A dot modules M dot, N dot, and P dot. Okay, so this holds true. Moreover, you know that homomorphisms from over A dot from M dot to N dot are the same as homomorphisms over some other algebra B dot, M dot over A dot with B dot, N dot. So for a morphism of DG algebras. So yeah, you can move things over to B dot and take the homomorphisms as A dot modules. This is compatible. Okay. Now, not only you can do this, because everything here, modules together with rings and so on, are Z-graded, you can also define notions that you have seen in the working with objects in the derived category, like for instance shifting, this notion of shifts or cones. You can do that too. So cones, given a dg a dot module, let's call it m dot. Module m dot. The shift m dot 1 is defined by shifting the underlying complex of k vector spaces so what does it mean? Of course, you have m dot and you shift it by 1 and you wanted to look at ith term, this will be just mi plus 1. But more importantly, this is the thing, d, if you shift a complex, if you shift a module, d of the shifted module will be minus d of the original module. Okay? And we know why that is, because, you know, your differential has degree 1, and each time that you apply the differential to an element of some graded piece in here, you scale it with the sign given by the degree of that element, an odd and even, odd and even, odd and even. So it makes sense. So shifting this changes the sign of the differential. Okay. The shift is again a dg a dot module in a natural way. Now that you define the shift, you can also define the notion of cones. So the cone over a homomorphism over the homomorphism phi from m dot to n dot of EGA dot modules, okay, is defined by so so cone complex of phi, which is the cone of m dot to n dot, is defined by m dot plus m dot shifted by 1. This is what the cone is. Thus, cone of the morphism m dot to n dot is again dg a dot module, and there exists a natural, or canonical triangle which takes you from m dot to n dot, and then the cone, and then the m dot shifted by. So this when you work over the category of DG modules, the category itself is a triangulated abelian category defined by this notion of shift. So it has triangles. Whereas, of course, you wouldn't get this when you're working with commutative ring functions or modules of a commutative ring, unless you move to the derived category. So this ring of functions on the DG-graded algebras itself starts from having extra structure in comparison with the ring of modules over a commutative. Yep. So now, two morphisms of DG A dot modules, let's call them F and G, from M dot to N dot, are called homotopic. I mean, we did construct these derived stacks and things like that as homotopical objects. So same applies in here. So they're called homotopic if they are co-homologous. As cocyclics. What does that mean? I.e., if there exists a morphism, let's call that morphism S from N dot to N dot shifted by 1, okay? Oh, sorry. M dot to N dot shifted by minus 1. Okay. Of A dot sharp modules such that this condition is satisfied. D of N dot acting on S plus S acting on D of N dot is equal to F minus G. This is the definition of the two maps being cohomologous. So take some element in here and if this condition is satisfied, then you have the two being homotopic. The two morphisms. It's pretty explicit. Okay. So now, by the way, there is a notation. So notation. So if let A dot be an associative DG algebra, then a left A dot module M dot is called quasi-free. If the underlying K vector space of M dot, graded K vector space, is free A dot sharp. A dot sharp is a free A dot sharp module. So as a graded module, we would like to say that M dot has a description like A dot over the underlying field times some E dot, where E dot is some K graded K vector space, right? So this is K vector space. It's a free module. Call it quasi-free. K vector space of okay. E dot is some graded K vector space of, well, depending on M, of generators. Depending on what's the dimension of M over A. Okay, so then you have this notion of quasi-freeness, exactly like freeness as before. Now there is a proposition. So let M dot and N dot be to Z graded left DG modules over A dot, and suppose that one of them, for instance, M dot, is quasi-free, and N dot is acyclic in degrees I less than 0. Remember that these are complexes, right? I can discuss about acyclic complexes. So suppose that this is quasi-free and one of them is acyclic in degrees less than 0. Okay. Then let us assume that F and G, again, are two maps between the free module to the acyclic modules bounded below the DG morphisms. Then what happens? Which induce the same morphism H star of M dot to H star of N dot. If this is the case, then in the sense I mentioned above, then F is homotopic to G. One of them is free module over the DG ring. One of them is acyclic below some degree. If the morphisms induces, if you have two morphisms between the two graded modules, which induce the same morphism in the lower homology, then that implies that the two morphisms are homotopic in the sense I described them. Okay, so this is some kind of a condition, but you will see the use of this later when we do schemes and so on. It has some nice and interesting corollaries. Okay, so I have very little time left, 5 or 6 minutes. There are certain corollaries. So actually proof of this thing is by this proposition. Proof is by induction. Proof by induction. I'm not going to. So corollary one of this proposition is that if M dot is a quasi-free DG M dot module, which is bounded from above and which is exact with respect to its differential. Okay, so if you have something like this, then m dot is, this is an expression, then m dot is contractible, called contractible. What does it mean? This means that somehow, in the sense that I described before, it can have some identity map on m dot can be homologous to the zero map, or homotopic to zero. So it means that, i.e., its identity map, is homotopic to zero. Okay. So the proof of this thing is that you apply, the proof is you apply this proposition that we had there to m dot being equal to n dot, and you pick for your map f the identity on m, and you pick for your map g 0. Then you can prove it. Using the proposition, you can prove this is thing. So this would be the what is called the contractible DG module, homologous to 0. Means that its identity map is homotopic to 0 in the sense I defined. Okay, so if that is the case, then there is also this other corollary, corollary 2, a quasi isomorphism f from some a dot module, some n dot module, a dot module n dot of both quasi free bounded above DG modules, DG a dot modules is a homotopy equivalence. Again, it uses the proposition. The way you show it is that you have this morphism of a dot modules, and you look at the cone, and then you show that the cone, in the sense of that corollary, will be contractible to 0. So proof is by showing cone of f is contractible using the proposition. Okay, so that's that. Then the last corollary. Yeah, so we are right on time. Corollary 3, consider DG modules consider corollary 2 situation in corollary 2, and then this is better. On the strain of corollary 2, then the dual morphism well, I call that one F, so the dual morphism is called F pullback, F star, F upper star, from homomorphisms over a dot modules n dot a dot to homomorphisms A dot modules M dot A dot is a quasi-isomorphism. Oh, so this is fine. So this is basically using the fact that this F is a homotopy equivalence, and the F upper star is a homotopy equivalence because its construction of F upper star is functorial. Next time, we are all done with the DG rings and modules. Next time we do DG schools. Okay. So I think we are done here. So any questions? And we have the seminar. So.